let's start with step 1. Normally, we'll start by creating some infinite lines horizontally, which will represent the surface that your robot will stand on, which is the floor. You need a few of these lines to represent the different views. You can get one to be the view from the side, one to be the view from the front, and one to just zone out different stuff. You can get the view from top down. You can zone out the different mechanisms that you might not include in your robot. That is for basically all of your backup plans and the additional informations. Then you can start adding in different components of the field. So in this case, I'll start by adding in the tower. So you would need to add in all of the numbers included with each game piece. So in this situation, for tower, I would need to include the size of the hole, the height of the tower, the size of the inner hole, the size and the location of the lower hole, and all of those numbers. One thing to keep in mind is that normally competition includes both the metric and imperial numbers for all of their calculations, but you would normally use the imperial if your competition is in the US, because the metric number is usually rounded up, and you don't want to use rounded up numbers for all of your calculations, because in the long run that will lead to a lot of errors. Trust me. So I'll get you a more detailed example of just how to represent the game field pieces on your sketch. So here I will sketch out the control panel, basically the disk for the FRC 2020 game. So I can just start out by drawing the view of it from the side, because that's normally what you need to do all your calculations. So just draw a rectangle to represent the side of the table, and you also represent the disk with another rectangle. Then you start adding in all of the numbers. As you can see here, I start by adding in the numbers related to the disk, because actually that is the main part. The table doesn't really matter except when you specifically include some kind of weird strategy with it. But as you can see, it kind of flipped, so after a while I just scratched that idea and just add in all of the numbers related to the table. Sometimes when you add in these numbers, it might turn out weird like that, but don't worry. If something's wrong, just cut out one or two numbers, add in all of the other ones. It will turn out fine when you add in all of the numbers. Don't worry. Okay, after you get all of the numbers related to the field in, you would want to start drawing out your mechanisms and entering in numbers that you cannot change for your mechanisms. Numbers like basically the size of the wheel, the size of the game piece that you're interacting with, all of those things. Another thing that you would need to define here is basically your goal. For example, as we're drawing a shooter mechanism here, I'm drawing out the trajectory that I want, and basically by drawing that out, I'm drawing out the space between which my robot can actually score the goal. I'm representing the trajectory of the closest point and the furthest point with two lines, as you can see here. Because we're using a two-wheel shooter, I expect it to fly out pretty fast. That's why I'm just using a straight line to represent the trajectory. After that, I start sketching out the actual mechanisms. I start by just drawing out some lines to represent the general shape. Then I draw in the game piece, the ball, and also I drew a rectangle to represent the wheel. This mechanism is, as I said before, going to be a simple two-wheel shooter, but you can actually change the angle of it by changing the distance between a point on the actual robot and a specific point on the shooter by unscrewing a long big screw, which will be connected to a very slow motor. Really, what I want to figure out with the sketch is the actual numbers I need for the screw, because if the screw is too short and you only needed to travel, let's say like 2 centimeters for it to change the angle between scoring from 3 meter and scoring from 7 meters, it would not be good because the error is going to be too big. I want it to be, but I don't want it to be too short, so the error will be very big. I want something in between, somewhere that maybe I can change like 20 degrees with around like 7 to 10 centimeters. I think that would be fair. So I just start entering in all the numbers, drawing out the general shape of it, and I'm keeping the distance between the specific point on the robot and the specific point on the shooter as a driven dimension, so that when I change all the other numbers, that will be changed. So in step 3, after you have drew out your mechanisms, drew out the numbers that you actually can't change, you start tweaking your numbers. This can take you from very, very short, like maybe only 20 minutes, to taking a long time. Trust me, in this case, I only changed like 2 numbers, one of which I can't really change much because the size of the robot actually kind of restrict it a bit. I'm just changing basically the point on the robot that the screw is going to be originating from. So I'm just changing that point and see how the other numbers on the screw going to be. Mostly just the distance that the screw need to unscrew to change the angle. Basically, from what you see here, I got it within like 2 tries, but for some mechanisms that are more complicated, for example, if you're using things like a turret with a flywheel, you need to change a lot of numbers. You need to draw out totally different things. For things like climbing mechanisms, you would need to draw out and change a whole lot of numbers. But for this case, you just need to tweak the numbers a whole lot. After a few tries, I got the numbers that I want. But normally, you would not just stop with one number. You need a whole table full of numbers so that you can do your actual prototyping. To get you another example of how to actually sketch, I will run through footage of me just sketching out this same shooter mechanism from the top down to get in some other numbers. So what I want to figure out here is basically the distance between the wheel so that the ball can shoot out with, well, optimal strength. So the rule of thumb that I was taught is basically to get the distance between the wheel to be about like 3/3 of the diameter of the ball. But because for the FRC 2020 game, the actual ball is pretty soft, you can deform it a whole lot. So I actually went with a bit less than 3/4. The ball is 7 inches in diameter. The distance between the wheel is going to be 5 inches. But the thing is, because this sketch is only for the prototype, or maybe the first time that you're manufacturing your robot, you want it to be able to change a bit. You don't want to just basically have to manufacture a whole new part just to change like one single number. So that's why the position of the wheel is not going to be static. Basically, I'm drawing out some slots so that they can move around, and that also needs some sketching to do. So basically, I'm drawing out some can you cut the previous sentence? So basically, I'm drawing out some slots so that the motors and the wheel can slide in and out a bit. So, and that also needs a whole lot of sketching. So as you can see here, I just draw the basic numbers like the thickness of the aluminum, the wheels that I'm going to use, the size of the ball. Then I can start figure out all the other numbers. Basically, the motors is going to be on aluminum piece, a small piece only, and that piece will slide along a frame that is going to be the actual shooter. Okay, as you can see here, when drawing out the slots, there are a few things that you need to consider. First, you would need to consider the size of the small piece of aluminum so that it can fit all of the slots without deforming too much. your motor is going to spin a whole lot. It's going to work for a long time. There's a chance that it will deform the metal, and you don't want that to happen. So you want all of the walls to be a bit thick. Normally, I don't want any part of the aluminum to be less than 3 millimeter, and that's basically what I'm doing here. I'm drawing out all of the slots I need, and then I make it so that they are spaced 3 millimeters away from the walls. So what we need here is basically a central slot, the biggest one, for the actual axle of the motor. Then you need 2 on the sides, or how many ever on the sides, to attach your motor to the actual plate. And then you need 4 or so more to basically make the slots for the plate to slide on your actual frame. As you can see here, I have a big one in the middle, 2 on the sides, and I'm just now drawing 1 in the corner so that I can mirror it to all 4 corners. I need to change the size of the aluminum piece a bit so that it can fit everything without breaking too much. Also, when you're drawing out this, you should also draw out basically the slot on the actual frame itself so everything can slide around. Okay, so let's hit it off with the easiest thing in the world, pocketing, because this part of the CADing process is basically just finishing up your robot and maybe integrating your backup plans. You want to get in all of the details. So one of the things you need to consider in your competition is like things like weight and size. Basically, if your robot is a bit over in weight, you need to do pocketing. Pocketing is just the act of cutting out parts of different extrusion and different parts of the robot to reduce the total weight. It can also give you a lot more space so that you can put in different parts, maybe like get an axle through somewhere, things like that. This can be easily done with things like hand drills. You can just cut out some circles, and that will be the first thing I teach you here, just how to draw out circles. This might seem simple because, well, yes, pretty much it is very simple, but there are a few things that you need to consider. First, the points of attachment with different parts. The thing about this is that when you're cutting out things, you don't want to cut out parts that are too close to the holes that you're going to attach to different parts, because that will weaken the connection point. So first, you just zone out the area around all of the holes and attachment points. As you can see here, I'm drawing out some construction lines to just zone everything out. Then I can start drawing some actual circles. This basically is just a representation of what you would normally do with your hand tools. You don't need to put this in your CAD. Yes, it will be helpful if you just basically do it since the beginning, but there's nothing wrong with just using hand tools for that. Basically, if you're using hand tools or CADing it, it doesn't matter. You need your numbers to be the same as one of the tool bits that it's available to you, or else you would need to do really stupid stuff like drilling and then using your drill to spin around, which will take a lot more time and will be a lot worse. And you don't want that to happen, so put in real numbers like 30, 29, actual numbers of tool bits. Just basically use the pattern function to copy off the circles around, make sure it doesn't interact with the area that you zone out, and that's basically it. This is the simplest way of pocketing. You can do it with hand tools, you can do it with CAD in like 2 minutes. It doesn't take a lot of effort, but it's not the best way to pocket. First, it's not the strongest way, and second, you don't get a lot out of just pocketing like this. It doesn't reduce the weight by that much. So that's why after this one, I will show you the next way to actually cut it out, the way that you're going to use when you're planning forward by pocketing in your CAD file. Okay, so now I will show you how to actually integrate pocketing into your CAD file. So one thing that is good with CAD file is that it's going to be used by CNC machines, which means that you can use the strength of different CNC machines. So when you are using hand tools to pocket, mostly you can only get to cut out circles. But if you're using CNC machines, you can cut out different shapes. And in this case, we're going to cut out triangles. Why triangles? First, cutting out triangles will make it actually a lot lighter than just cutting out circles. You can get out a lot more from corners. It's just a lot lighter. Another thing is that cutting out triangles makes it pretty strong, unlike cutting out circles. If you're cutting out until you have the same volume with circles and with triangles, the triangles is going to be a lot stronger. The thing is, when you're a triangle with the 3 different lines static, you define the length of all of those 3 lines, all of the angles inside cannot be changed. It will be static. You cannot do anything about that, which makes it a lot stronger. It's evident in things like bridges and different structures. You just see triangles to support things basically everywhere. So first, just define the place that you want to cut the materials out of. In this case, I will just cut out one corner of it because the rest will be basically the same. So first, define the middle. Draw a line that is going to be 60 degrees from one of the sides of your extrusion, and then just start drawing out the triangles. The only number that you need to define here is basically how thick you want the sides of the triangle to be. So in the case here, I put a side as 5 millimeter because it needs to hold quite a bit of load. So then you just start drawing out triangles. It's going to be regular triangles, which means that all 3 angles are going to be 60 degrees. So you just want to draw out 2 triangles that are going to be mirrored through the point in the middle of the part that you're going to cut out, and then just start linear patterning, or also called rectangular patterning, it to 2 sides, and then just cut it out. This is the actual way to integrate pocketing into your CAD. You can see it used by a whole lot of teams. Every team cut out different triangles. That's just what everyone does. So why not also do it? Next, after you're done with pocketing, you also have the concern of durability. So of course, there are going to be parts that will receive significantly more stress than others, since not every part supports the same amount of things, and not every part moves around in your system. So for support, just support the parts that are connected to the base because they will bear a lot of load. They basically need to carry the whole weight of your robot. Also, support parts that are going to be directly attached to some spinning axles because they are going to move around a whole lot. There's going to be a lot of backlash. They will get loose very easily from constant movement, so please support them. And another thing that you need to support is parts that are overhanging a bit too much. Basically, just count the number of parts in between that thing and your base. If it's larger than the numbers of every other part, probably it will need support. So generally, everything will have a bit of backlash, and the further away it is from the support, the more backlash it will have, which will be a really bad thing because it will mess up with your calculation a whole lot. So you need to support all of these different parts to minimize backlash, to minimize damage to your robot. So I will now name some things that are normally used for support. There are going to be guides, flanges, and gussets. So guides are things like grooves or sliders that will help your mechanisms move around a whole lot. So basically, it's similar to that thing that we drew in episode 6, the second part of the first cat episode. So basically, guides are things that will help you move around, but will also limit your movement in a certain area. So as you can see here, is basically just a groove so that you can slide things along. Then you have a gusset. A gusset is basically just a sheet of metal that is used to connect different parts. It might seem simple and might not seem very important and very impactful, but the thing is that a gusset is not that heavy and you can get a lot of them out. Basically, they're robots that are just connected with a whole bunch of these. They're bays that are just a whole bunch of these connect together. The strength of this is in numbers, and the places that you can fit it in is smaller than integrating guides, is smaller than integrating different support mechanisms like just a support beam or flange. That's why it's very useful. Basically, if you see two parts that are close to each other or on the same plane, you can connect those two with a gusset. Lastly, you have support beams or flange or whatever you want to call it. This is basically the simplest thing that you can use for support. Just pump out, well, a whole beam to support that part. Basically, like I said before, you don't want parts to overhang too much. So why not just use like a huge support beam to just connect that part to the base? That is very simple. It's a very direct change, but normally you would not want to use this too often, because if your robot have like 20 different support beams, it's going to be very heavy. So basically, you only need like 3 or 4 of these around your robot to support the whole thing, and then just starting connect everything to that.